this mean it's warmed up?
Mm-hmm.
Okay. Hi guys. If I could just have your attention for a quick second, I just wanted to remind y'all that there's a climate strike at 11 on Norland Quad, inspired by the Fridays for Future by Greta Thunberg. So please show up. The time to act is now. Thank you.
Okay, so I'm going to get started. The announcements for today are that Chapter 2 Sapling is due 9 a.m. Wednesday next week, which you'll notice is about 12 hours after the exams, so of course I recommend finishing it before that point. Chapter 3 is also open. And speaking of Chapter 3, I might not finish the entirety of Chapter 3 material. It's looking like the last couple pages of the notes I probably won't get to, so like predicting acid-base relative strengths. But I will cover the rest of Chapter 3 on the exam, so I'll draw the cutoff after Monday's lecture once we get wherever we get to. So then the exam review is going to be Sunday, 3 to 5 p.m. in Duane G1B20. I don't have any material planned out for my exam reviews. I always just show up and answer questions that people have. So those might be questions from Sapling, questions from their recommended textbook problems, questions from the exam archive, or just like theoretical questions about the material that you may have sort of been wondering about. So feel free to show up, bring whatever questions you want to go over, and then it'll be lecture captured for those who can't make it. And then the exam itself is Tuesday, 7 to 9 p.m., Chem 140. Model kits are allowed, but no open books, no open notes. Okay, questions about that? Okay, those of you with accommodations, I'm still trying to get the room sorted out. We may have to do sort of a change from the one I was originally assigned just to accommodate some people with extra accommodations, so we're still trying to get that figured out. I'm hoping I'll hear back from them by like later today. Okay, cool. So, where we left off last time in Chapter 3 was we're looking at curved arrow notation. And the ways that we can use curved arrows to show electron pairs traveling around. So I sort of mentioned that I sort of reordered my notes and didn't catch that I put something in the wrong section. So just to summarize the 3 different legal moves. Okay, so first is lone pair on an atom becomes a bond to that atom. Second one is the other way around. Bond to atom becomes a lone pair on the same atom. And then the third one is bond to bond. So bond to atom becomes a different bond to an atom. Okay. So here's one example of a bond to bond move. And I started drawing this up last time, but I didn't get to finish talking about it. So we've got boron here with 4 H's on it. This is a borohydride anion. We're going to be hearing from this one in OChem 2 a bit. It's got a negative charge on the boron according to formal charge, but if you look, it doesn't actually have any lone pair on the boron. If you count electrons, there's no way to fit a lone pair on there. So all the electron density in this thing, it is like an electron-rich species, so it's going to be the nucleophile, as a kind of reminder there. But the electron-rich area isn't a lone pair. It's pretty much all the electrons this thing has to spend are in BH bonds. Okay, so if we introduce an electrophile for it to react with, say something like, this was one example of what I used last time. We know that this structure has some electron-rich and electron-poor regions. Oxygen is more electronegative than hydrogen. Hydrogen is going to be delta positive. So H is electron-poor. So that's going to be our electrophile. It's getting attacked during this reaction. Okay, so we send our electrons from the electron-rich regions. We can just pick one of the BH bonds. We have the arrow come out of here, go attack on whatever the electrophile is, the hydrogen in this case. If that were all that we showed, so I'm going to leave it like this for now. That's not correct because I need to do something else, but let's hypothetically say, what if we left it at that? Gesundheit. Okay, so what if we only showed this arrow? Well, in that case, we would have the electrons from the BH bond that broke are now gone. So that boron now just has the 3 BH bonds left. If you check for formal charge, its negative charge is gone. But we've now made a new H bond, but nothing else has changed the way that I drew it based on the arrow pushing over there. This should look very, very bad and wrong to you because that has 2 bonds to the hydrogen, or violating the hydrogen's duet rule. Okay, so obviously this is a no-go. So in order to fix this, at the same time we're doing the attack, we're going to have something else happen so that hydrogen stays under the maximum. So this will be something that you see very frequently where you go do an attack on something, but in order to stay under its duet or octet rule, you've got to drop something else off of it at the same time. So this nucleophile attacks the H, and at the same time, H kicks out the OH there. So that gets us to boron has now lost its H again, so it's down to 3. It's neutral now. We now have a new H bond here, and we've got a free-floating OH hydroxide that got kicked out. Okay, so a few things that are worth pointing out here. One is that if you want, you can go through, check formal charge on everything, and you'll conclude after some numbers crunching that the OH is the one where the negative charge ends up. But you could just as well save yourself the work and say, okay, I know boron started out with too many electrons. It gave up electrons because I have an arrow going away from it. So boron should end up neutral after that. And when I follow this chain of arrows along, oxygen is the one that they end up at. So oxygen should be the one gaining electron density in that exchange. I think I saw Hen go, yeah. No, they're all equivalent, so any of the 4 I could have picked. I just did the one that was like easiest to draw from where I had it. Yep. Okay. So other questions about this? Okay, so here's the example that I mistakenly put in section 3 when it should have been in category 1. and that is, and I'm going to fix this for next year's notes, but I figure I'm not going to update them as we go along during the semester because then I have to deal with multiple versions floating around. Okay, so here's an example where OH minus comes in, attacks carbon. If that were all that happened, I would end up with 5 bonds to carbon, which is clearly a no-go. So to avoid that, I have to, at the same time, kick out whichever group on the carbon is most kick-outable. So we're going to talk a little bit more about how easy it is to remove different groups. It really depends on how stable they are on their own once they get the boot out of that molecule. Okay, and again, oxygen was electron rich, but it gave up some of its electrons to form that bond, so you'd expect it to be neutral afterwards. Bromine was neutral. It ended up getting some electrons from this, so you'd expect it to be negative charged. And you can check that by going through and calculating formal charge on everything, but you can also just not have to go into that level of detail. Another thing to check, -1 charge overall for this whole deal, so we should have -1 charge overall for this whole deal. Very useful to check that. And then one last thing that is sort of worth pointing out is that this group here that gets kicked out, this is what's called a leaving group. So how to tell a leaving group? I'm trying to indicate that I'm talking about the BR here without actually drawing an arrow because that indicates electrons flowing, which I don't want to do. All right, so that BR is a leaving group. I guess I don't remember if it's Loudon or a different textbook, but it describes leaving groups as groups that take the electrons out of their bond and leave. So it specifically has to end up with the electrons out of its bond. Okay. So any questions about any of these examples? Yeah. Excellent question. Because based on the arrow pushing that we have, that would be an equally valid way to show arrow pushing. Really, it comes down to if I kicked out the BR, how stable is the BR with a negative charge on its own, versus if I kicked out one of the H's, how stable would that be with a negative charge on its own? And that's what we're going to spend most of today looking at, actually. Yep. Okay. Question? So those tend to be quite rare just because the more charge you have concentrated in one place, the less stable it is. So I don't think we're ever actually going to see like multiple positive or negative charges until we get into transition metal chemistry, like way into OChem 2. Yep. Okay. So other questions about these examples before we move on? Yeah. So that's actually the next section I'm going to cover. Sorry, you guys are like way ahead of me. Nice. Okay. Oh, and I didn't set the camera. Sorry to whoever's watching this. I'm going to move the board down. Right, there you go. And moving it up. And there. Okay. Cool, cool, cool. Oh. So one last example that I did want to show here. Actually, no, I'm going to hold off on that until I get to a section a few parts in from now. Okay, so actually getting back to your question, and that is how do I know which of these reactions involve acid-base, like Bronsted-Lowry acid-base, and how do I know which ones involve Lewis acid-base? So bases versus nucleophiles is a topic we need to look at. So I'm going to put up two reactions here that are going to look really similar. Both of them have an OH minus. And both of those OH minuses are attacking something with a Br on it. So in this case, they're going after an H, kicking out the bromine. In this case, they're going after a CH3, kicking out the bromine. And in both cases, they end up with a new attachment to that group, and you end up with a Br minus bromide anion as a leaving group. Note that I'm writing it as H3C here and CH3 there. It's the same thing. You can write it either way around. I guess traditionally you would show the carbon like right at the end of the bond of whatever it's attached to, and then the H's just follow, but it's not too important either way. Okay. So two different reactions, very similar to each other. One of these reactions involves an H changing hands and not getting to bring any of its electrons with it. So H, or in other words, a proton, gets passed from one molecule to another. Even though it doesn't actually take on a positive charge at any point, we're still calling it a proton because it never gets to bring any of its electrons with it. It just loses what it has, and then at some point it has new electrons coming in. Even if those are simultaneous processes, which they are here, we're still calling it proton transfer. So this one is called a proton transfer, which tells us that this is actually falling under the purview of Bronsted-Lowry. This is actual proton exchange. Something is acting as a Bronsted-Lowry acid. It's this one because it's giving up an H+. Something is acting as a Bronsted-Lowry base, this one because it's accepting an H+. So this is an acid, and this is a base. So reminder that when we just say acid or base, we specifically mean Bronsted-Lowry acid or base. It's something where a proton has to exchange hands for it to be considered an acid-base reaction. Okay. So, and I should have drawn these a little bit further apart, sorry. But by contrast, this one down here, we don't have a proton that's getting handed off anywhere. Technically, you could see it as like this CH3 group is getting passed around. But because we tend to do things more from carbon's point of view, you could also see it as carbon here is choosing to drop its bromine and accept a new OH group on there. Either way, when we do the attack, we're attacking anything other than a proton, usually carbon. So if we attack anything other than a proton, then this is a nucleophile-electrophile reaction, or Lewis acid base. Okay, so if we're throwing in labels, this would be the nucleophile, the OH minus, and this would be the electrophile, the CH3 with the BR on it. Okay, so pretty much the easy way to tell, am I looking at Bronsted-Lowry acid base or Lewis acid base, is there a proton getting shuffled around somewhere? Question?
Is it valid to say that if the curved arrow ends and like kind of points to an H, it's a Bronsted-Lowry?
Yeah, that would be a correct conclusion. So if an arrow anywhere like ends up pointing at an H, and then that H has to drop whatever it's already attached to, if anything, then yep, that is an acid-base reaction. Did I see a hand up back there? Nope. Okay, cool. Okay, so that's how to tell the difference between bases versus nucleophiles. You'll note that in these two examples, the OH is actually doing each job once. So OH can act either as a nucleophile or as a base. And this is going to come up again multiple times in the future, where things can be nucleophiles with varying degrees of being good at it, and they can be bases with varying degrees. So something might be a really strong base and a good nucleophile. It might be a strong base and a poor nucleophile. It's sort of independently variable, like how good it is at doing either of these jobs. But it's sort of like a role the molecule can play. It's not like this molecule is inherently a nucleophile or is inherently a base. It's just sort of, it could do either one depending on circumstances and how good it is at either one. Okay, questions about that? Yeah?
So why is the CH3 the electrophile versus the bromine and bromine has negative charge?
So the bromine has delta negative charge. So I guess like it helps to look at in your starting material where is the polarity kind of pointing. And so carbon, you know, has a delta positive charge in this bond just based on electronegativity. So carbon's going to be the electrophil, I guess what we would call the electrophilic site in that molecule. Labels get a little bit hazy. You could call the entire molecule the electrophile, but really the one position that's actually going to get attacked is the electrophilic site, which is the carbon. So, okay, cool. So tying this back a little bit into molecular orbital theory, we can actually look at where the orbitals are coming from, or where the electrons are coming from and going to. So Fmo theory. So frontier kind of means like the outermost part of the electron cloud around the molecule that's reacting with other molecules. So it's kind of looking at when we actually start doing these reactions, not only do we have to worry about like the molecular orbitals in the molecule, we have to worry about which one's actually going out and doing stuff. Okay, so during a reaction, electrons are transferred from what's called the highest occupied molecular orbital which gets abbreviated as HOMO, into the lowest unoccupied molecular orbital, which gets abbreviated as LUMO. So you're transferring electrons from the HOMO to the LUMO orbital. So we can pretty much take this and apply it to some of the examples that we've seen over here. So I guess these examples are not exactly the same as what I used for examples of arrow pushing over here, but it's kind of good to see some more cases. So, okay, so we've covered like ET is short for an ethyl group with an O- attached to it. Okay, so in this case, it's pretty similar to up here. We have a negatively charged oxygen. This is the nucleophile going in and attacking this molecule, this electrophile here. So ETO-CH3 and then Br minus. Okay, so the electrons are transferred from the HOMO orbital. So you want to look for wherever the arrows start, the nucleophile in other words. So where exactly are these electrons coming from? They're coming out of the lone pair on oxygen here. So electrons are coming from the lone pair on O, which means that the highest occupied molecular orbital where the electrons are coming from is the non-bonding orbital on oxygen. And then where are they going to? This part's a little bit trickier a lot of the time. Okay, so there's not an empty orbital on the carbon here. At least like there's not an unfilled octet to put it in. But we do know that as a result of doing this attack, whatever is going on at this molecule results in the carbon-bromine bond getting split up. So another way to look at it is the carbon-bromine bond order has to go to 0 when we throw more electrons into it. So what's actually happening is, and I'll draw up an Fmo diagram, just like a quick sketch of part of one to show what I mean in just a second here. But because we're breaking the carbon-bromine sigma bond, we're putting more electrons into the anti-bonding orbital, which means that the LUMO is sigma star of the carbon-bromine bond. Okay, so I didn't include in the notes a drawing of how that would look, but just in case you're curious, here's our little example Fmo diagram. All right, so we got our sigma star. All right, so ignoring all the H's on CH3Br for the time being, just looking at the carbon-bromine system by itself, we got just a regular sigma bond between them, and there's 2 electrons in it, which means we also have this sigma star antibonding orbital sitting empty. If the molecule were just sitting around by itself, this would be pretty much all you have to show. But as soon as we start throwing extra electrons into the system, say from a lone pair on oxygen, 2 new electrons come in, they dump into this system, and now all of a sudden my bond order goes to 0, and that CBr bond doesn't exist anymore. So that's kind of an Fmo way of looking at what's happening up here. When I break that carbon-bromine bond, because I'm adding more electrons to the system, that's kind of what's happening orbital-wise. Okay, I guess I should specify carbon-bromine sigma bond breaks because we're putting electrons into the sigma star antibonding orbital. Okay, so the LUMO, pretty much you want to look at the electrophile molecule, see if there's any bonds breaking as a result of the attack, and then if there are, then you just say, okay, it's the antibonding version of whatever broke. And that's how you identify the LUMO. Okay, so the reason this is important is because the actual shape of the orbital sometimes dictates whether this reaction can actually happen. We'll see some examples of the LUMO is actually sticking out one particular direction from the molecule, and you have to be able to attack from that direction if you want to be able to do this reaction. Question?
What if it were a free radical? Would it break the bond with a half?
So yes, but at that point, yeah, I guess we tend not to get into Fmo diagrams for single electron transfer stuff just because it's a little bit more comfortable. Pretty much we're just dealing with like pairs of electrons for the time being. So, okay. Okay, so a couple more examples here. Okay, so here's one where let me actually explicitly draw that as a carbon for the time being, just because people are still getting used to skeletal structures a little bit. Okay, so here's one where ETO minus, ethoxide, comes in and attacks here, and we break the CO bond. And as a result, we end up with OET attached on here, and that double bond that we used to have, the CO, has gone to now a CO single bond. And just to double check, we had a minus charge overall. We should have a minus charge overall. Yep. And then this thing lost electron density. It should drop down from negative to neutral. Meanwhile, this oxygen up here was sort of on the receiving end of that electron flow, so it should end up with a negative charge at the end. Yep, looks good. Okay, so identifying Homolumo here. This part is actually just the same nucleophile as what we used up there. So it's exactly the same non-bonding on oxygen. And then the LUMO. Okay, so what bond am I breaking when I do this attack here? Pi bond, yep. Yeah, I'm going from a double to a single bond. So I'm losing a pi bond, which means that I must have dumped electrons into the pi star to make this happen. Yes, I'm going to see if I can squeeze it in down below this one, actually. Okay. Okay. So we know that both these atoms, the C and the O to start out with, are sp2 hybridized. So we've got, both of them have one unmixed p orbital and then 3 hybrid sp2 orbitals. So the p orbitals are what we use to make pi bonds. That's kind of why pi is the Greek letter for p, actually. Okay, so pi and pi star come from using the p orbitals, while the sp whatever, in this case sp2, make the sigma and the sigma star. And you'll notice that p orbitals are always closer to each other than, pi and pi star orbitals, sorry, are closer to each other than the sigma and sigma star orbitals. And that's just because there's kind of less energy at stake with side-on overlap. Like, there's less to gain and there's less to lose energy-wise. Okay, so filling in electrons. It's a little bit hand-wavy for parts of this because, again, we have other stuff attached to the carbon. So we're not showing all of the CH bonds here. But we do know there's 4 electrons total in the CO system. So start filling in sigma, then pi. So there's our 2 bonds. Now if we come in with 2 new electrons and we drop them into the lowest unoccupied molecular orbital, that's this one, because it's unoccupied and it's the lower of the 2. So I'm dropping electrons into this pi star orbital, which means that the pi bond is going to break, and I'm going to go down to bond order of 1 instead of 2. Okay. So questions about that example? Okay. So I'm going to erase the other side of the board real quick and do a couple more. Okay, so a couple more examples. All right, so here's this borohydride again. I'm going to use this a few times because it's a good example of something attacking from its bonds instead of a lone pair. Okay, so here's one reaction that we've seen where BH bond goes out and attacks something. I'm using the same carbonyl CO double bond as before to get attacked. All right, so where are my electrons actually coming from here? I know that I'm not using a lone pair on boron because I don't have one. I'm actually attacking with the electrons out of the BH bond. So here, my highest occupied molecular orbital is actually going to be BH sigma, which I can tell because those are the electrons in the bond that I'm using to do the attack. Okay, the LUMO that's getting attacked is actually the same one as in the previous example. I know that, I guess it would help if I drew the whole thing. Okay, so I know that, again, I'm breaking the CO double bond, at least the double part of the double bond. I'm losing the pi bond when I do this attack. So LUMO is going to be CO pi star. Okay, so one more example. All right, so here's this product of this reaction up here, BH3. It's now neutral, so it's no longer electron rich. It's not going to go do any attacks. But it does have an unfilled octet on the boron. So anything around that's nucleophilic, like this O-, could come in. And this time I don't have to lose anything attached to the boron because it's got room for it. It doesn't have a filled octet already. So I can just show this as boron. Now boron's got the negative charge, and I have a new OET group attached to it because I just made a bond. Okay, so here the attacking orbital is, again, the lone pair on oxygen, or you could write it as non-bonding on oxygen. The LUMO, I'm not breaking any bonds doing this. I'm just dumping electron density into an empty orbital on boron. So in other words, non-bonding on boron is the LUMO. So non-bonding could be filled, in which case it's a lone pair, in which case you can do the attack. Or non-bonding could be empty, in which case it's a convenient place to dump electrons without having to break any other bonds. So it can be either the HOMO or the LUMO orbital. Okay, questions about that? Okay, cool. So what we're going to get into now is looking at another use for curved arrows that actually is going to make stuff from Chapter 1 quite a bit easier. And that is using arrows for showing resonance. Okay, so we've already seen in Chapter 1 that you can draw resonance as like multiple different valid Lewis dot structures of the same thing. But sometimes it's a lot of extra work if you want to figure each one out from scratch. So what we're using these arrows for is, like, if we start with one valid Lewis dot structure, can we sort of use arrows to shuffle things around a bit to maybe get us the other resonance forms without having to do it all each time? So the rules that we want to follow are obviously charge is conserved, so total number of electrons stays the same. So if there's an overall -1 charge at the start, there has to be an overall -1 charge at the end. Also, the same 3 legal moves that we saw up here, or earlier in the lecture, still apply. So lone pair to bond, bond to lone pair, or bond to bond are the only ways we can move stuff. We're not going to change connectivity. So all the atoms stay connected to each other the same way they are start to finish. What that basically means is that we can't use electrons from sigma bonds to do resonance. It turns out that you will sometimes see some cases where the sigma bond's weak enough that this sort of, it's a bit of a gray area whether it's actual resonance or equilibrium. We'll cover those examples when we get there. But for now, don't use electrons from sigma bonds is kind of a good guideline. So this means that we're only going to use pi bonds and lone pairs as sort of our puzzle pieces that we can slide around here. Okay, just like we saw in the previous examples, you got to obey the octet rule or the duet rule. So if you're trying to add electrons to something with a full octet, something's got to give. It's got to lose a bond somewhere else if you do that. And since we can't break sigma bonds when we're doing resonance, that pretty much means that we have to break a pi bond that's attached to it already. Okay, so once we've figured out our resonance forms, we can actually look a little bit at evaluating stability. So these last 2 bits concern that. So once we've drawn the resonance forms, the ones where every atom has a full octet are the most stable. Okay, so ideally what we're trying to do is maximize everyone's octet. If we're trying to compare beyond that, then we also want to minimize charges. So if all forms have the same number of unfilled octet atoms, then the ones with the fewest charges are best. Or failing that, the ones with negative charges on more electronegative atoms and positive charges on less electronegative atoms. Because we already know that's kind of what those atoms are into anyway. More electronegative atoms means they want more electron density, so giving it a negative charge is probably better than the other way around. Okay, so with this in mind, let's look at an example of how to use arrow pushing to show resonance forms. So an example here is C3H5 with a minus charge. Okay, so turns out that you can draw oh, sorry, that's a positive charge, not a negative charge. Okay, I do both in the notes, but I'm going to do positive first. Okay, so here's how this one turns out to look. You can draw it out explicitly as the atoms, or you can draw it as skeletal structure here. Okay, so what I'm going to do is follow the same rules from before, where I have an electron-rich area, which happens to be this pi bond, an electron-poor area, this absence of electrons, this positive charge. I'm going to take the arrow out of the electron-rich area, take the electrons out of this pi bond here, and I'm going to hop them over to here. So note that out of the three legal moves, I'm taking electrons out of a bond. I'm not going to create a lone pair on this atom, so I'm not going bond to lone pair, but I am going bond to bond. So remember to use your double-headed resonance arrow here, because that's what we're doing. What I'm doing is taking electrons out of this pi bond, and using them to create a new pi bond on the other side of the molecule. Okay, so again, this is a bond-to-bond move. The electrons were previously associated with this middle carbon, and they're still associated with the middle carbon afterwards. Question?
Isn't that the same molecule? It would just flip?
It is, yep. So this particular example, it happens to be the same as rotational symmetry, but this is kind of the simplest possible case of like a 3-atom subunit, and this is going to show up in a bunch of places as like a smaller part of a much bigger molecule where you might not still have that rotational symmetry anymore. Okay, so real quick, let me just show it on this example too. We can take, it's the same structure but just shown in skeletal format. So we've got this 3-atom subunit where it flips ends. Okay, so that's a good stopping point. I'll pick up there on Monday.